Hello, this is Advent of Code 2024. My name is Nawaman. I'm the author of functionalj.io. Functionalj.io brings functional goodies to Java, allowing us to write more functional startup code. Today's puzzle will be day 9. All the code discussed in this video, as well as all the links these pages, will be in the video description. Let's get started. Day 9 puzzle is about this fragmentation. We will be helping Friendly and Pribot organize their files. I'm not sure how can we help marine animal to organize their file, but let's go with that. So the input we're going to have will be called this map, which will be in this form. So these numbers represent the size of the segment of the files. So the first character represents the size of the file number 0. And then this will represent the size of an empty space after number 0. Then this one will be the size of the file ID1. Then this is an empty space. So the odd number characters represent the files, the size of the files, starting from index 0 to 1 to 2 to 3 to 4 and so on. And the even index number represent the size of an empty space between these files. We can see the expanded example here. So there are two segments of file index 0, and then there are 3 empty space, and there are 3 of the index 1 and 3 of empty space. Then there is 1 of file number 2, 3 of empty space, and so on and so forth. So in order to organize the files, we were asked to come up with a way to move the files from the back into the front. So we move 9 into this empty space, another 9 here into this empty space, because we only have 2 9, so that's done for 9. And then we move 8 to this empty space here. 1, just leave it there, and then the 3 empty space, we can put 3 8 right in there, leave the 2 there. There are 3 of the 7, can put it in there. So we do all this at the end. The file system will look something like this, right? So the file's content will only stay in the front, and then the back will be empty. The last step is to calculate the checksum. And the checksum is calculated using weighted number. The checksum is calculated using the weighted sum method, meaning that we will multiply the index number of the files with the position of the files. So this one, number 0, will be multiplied with the index 0. This one will be multiplied with index 1. This one will be multiplied with index 2 and 3 and 4 and so on. Look like this. 0 times 0, 1 times 0, 2 times 9, 3 times 9, and so on. In this example, once all said and done, the value is 1928. That's the result. That is the checksum of this compact file system, is what we were asked to calculate. So the way we're going to approach this is by expanding the disk map into a file system, and then we represent the empty space with -1. 2 will be 20 here because it's the size of the file number 0, and then 3 is 3 empty space. This 3 is the 3 slot for file index 1, file ID 1, and then 3 empty slot, and so on. So we expand that first. And then we create something called the files in reverse, which is basically the list of the index of the file. So this is file 99, and then 888, and then 777 in reverse. In other words, we remove all the empty space and reverse it. So we get 99, 88888. And then we convert this into an iterator. An iterator is a thing that we can ask for its next item. So then we can go through our file system, and every time we see a -1, we can ask the files in reverse iterator for some items. First we get 9, we put 9 in there, and then we get 9, put 9 in there, and so on. Every time we see -1, we ask this iterator for the number. And when we stop, well, we stop when we reach the number of the file content, which we calculate in advance. Forgot to write here. So we calculate the file system in advance by going through all the odd number and then sum them. Or another way, we can see that it's a number of items inside these things. In this case, it's 28. So we will only go to 28 slot, go through that. Every time we see -1, we just ask the iterator for the next items. Then we can fill the file system to make a compact file system into this. And the rest here will be empty anyway, because we assume that we pull everything from there. So it will be empty. From here, we can calculate the weighted sum. Now let's look at the code. We will be getting the input from this parameter lines, which is the list of string, only the first one, and then we convert it to a list of characters, which in this case it will be int, because Java represents characters with int. Then we subtract each of the int with the value of character 0. The next step is to expand this input into a file system. To expand, we will create the file ID if the index is odd. So in this case, the file ID 0, there will be 2 of the file ID 0 because the index is odd. If the index is even, we just put -1 to it. So we first need to determine what number to put it in. So if it's odd, then we put -1. Otherwise, we put the file ID, which is the index, divided by 2. So this is for number 0, this is for number 1, so on. And then we limit it to the length of the files that we want. So when we repeat something, it will repeat forever. If you ask for it, it will give you the same number forever. But we don't want forever, we just only want the length of it. Then big flat map it. So at the end, what we get is just in up list, which is this here. Okay, that's the first step. The second step is to calculate the files in reverse and then use it as an iterator. So basically, we have the file system, we reverse it, we exclude all the -1, right? File in reverse doesn't have empty space, just only the files. Then we convert it into iterator. We can convert it to iterable, which means that you can ask for multiple iterator, but we only want one iterator, so we just do this one in one step here. Then we calculate the user space, which only loop through the index that contain the files, which is the event index. So we go to 0 and 1 and 2 and 3. So this we use the access called int, if it event. There can be one video explaining about access. Basically, it's a way for us to create the change of functions related to an integer in this case, and we can have long and stuff. So we don't need to write I and then we don't need to write something like this. We can do with that, which depends. If you like wordy, can be like this, but if you like symbolic, you can go like that as well. So I put both styles in here. And then after we get the index that is an event number, we can use it to get the value from this map and then sum them all. After that, we calculate the compact file system, which is basically looping through each element in the file system and check if it not equal to 0, that means it contains the file of each index. So we just leave it alone. So if it's not equal to -1, we just leave it alone. Otherwise, we replace the -1 with the content from the files in reverse, which is here. So we go from 998888777 and so on. And then we only use to this use amount. Because once filled, the rest is -1, which we don't want. And the last step, we calculate the checksum. And to do that, we just go through the compact file system, and then we just map the items with its index. The items is the ID of the files it's in. We time the index with the ID because -1 represents 0. So max of 0 and ID with always the ID or 0, right? Which we don't care. And then we change it to long because the number can be quite large in the production example. And when they multiply and sum together, it can be quite large. And at the end, we sum all the number. And that's what we got. Once run or pass, everything is good. That is for part 1. Part 2. In part 2, we realize that compacting all the files to the beginnings where the file contents can be separated because the available space, it's not such a good idea. So we use a different method. This time we go from the back again and see the files. In this case it's 99, and 99 required 2 position, 2 segment. So we go to the front and we see, hey, there are 2 available space here. So we move the whole 99 into this 2 available space. Then we go to the back again and we see that 8 require 4 items. So we go to the front and see there is no 4 available spot. So we do not move 8. And the next one is 777. Go to the front and we see that there are 3 spots available here. We can move the whole 777 here. Then we go to 6. Again, 6 have no space because it requires 4. 5 require 4, so they both can be moved. And then 4, we are here on this line now. So there are 2 4. We go to the front and see here is 2 available space, so we move 4 into this slot right here. Then 3 require 3 for files number 3, but there's no empty space in front of it, so we do not think. And lastly, we see number 2, which require 1, so we move this 2 into this 1 empty space. Once we get this, the fragmented compacted which file, we calculate checksum just like before, and this is the new value for this example. Let's take a look at the code. Well, there are 2 approaches to this problem. During the competition, I used the first approach, which is to expand the disk map into file system, but it takes hours to run. So later on, well, actually recently, when I have more time, I create the non-expanding method now here, which only take a few seconds to run. I'll explain more details for this after, but let me go through quickly how to do it with the expansion method. As the name suggests, we expand the file system, but in this case, we don't expand it into full list of array just like before. So before we expand this into this, now we will expand this into this instead. So as you can see, there are 2 of the file number 0, and there are 3 of empty space. There are 3 of the file number 1, and so on and so forth. So we get a list of array. Then from here, we know what index, what file index, and what is this size space. We can go to this array, which is a sector by ID. So it's a number 9, we go to number 9 and then copy the content size of 2 into whatever the available space we found. So that way, we can get the fragmented file system. But because this used array, so this is not fully functional because array is mutable and we use the mutability of it as well. So when we move 9 into this empty space, we actually modify this to slot as well as this one, change it to null. So, and because we expand it and there's a lot of copy files between arrays, so it takes hours to run. Now, the second method, non-expanding method. As the name suggests, we do not expand the disk map into the file system. Instead, we operate on the disk map and its derivative, which is much smaller instead. And the idea is this: we simply determine where the file's content will go. So the first thing, we go to all the file content and determine where it will go. We call this the move files. So from this map, you can see the file segment, right? File number 0 need 2, file number 1 need 3, and so on. Then we can determine where the file will be moved to because we go from the reverse. And we found that for file number 9, we need 2 space. And then the logic will determine that this 2 space will be moved to the available, what do we call? We move to the partition, right? So this is one partition. This is the second partition. Let's call user term partition. So user term partition, we go from the back of the file, which is the front of this reverse. So we see that we need file number 9 for 2. And this partition have already files in it. This partition is empty, right? So the first partition is partition number 1. We will put file number 9. We need 2 space into it. We mark it as a move. Then the next item is file number 8, which requires 4. We go to each partition and we did not see any partition with numbers 4. So we put the output, the move file, as at index 16. We will have file number 8 require 4 space and it's not moved. And so on and so forth. So go to 7. 7 can be in this partition, which is partition 3. This is 0, 1, 2, and this one is 3. File 7 will be there and it got moved there. This flag has moved is the important one for later thing. Then the next step is to determine all the space that was left when the file is moved. Because we know that some of these files are moved, we know where are empty space. So in this case, because file number 9 at the index 18 is moved, so the empty space there will be the empty space, which is the index 0, and 2 available, 2 empty space with number 2 here. So we try to adjust this to be the same data structure, but actually this is not used. That's why we put 0, right? And this is not used. The only thing that used is this index and the empty space, but we put in the format. So we collect all those because there are only 4 files that are moved. The next step is to determine space that was left unfilled. So in this case, this one are left unfilled. This one left unfilled, this one left unfilled, and so on. So we get 6 of that. Then we combine all these 3 together, and then we sort. We get something like this. So at the partition 0, we get file number 0 for 2 space. At partition 1, we get file number 9 for 2 space, and file number 2 for 1 space. At partition 2, we get a file number 1 for 3 space. File number 3, we get file number 7 for 3 space, and so on and so forth. After we get this, we can calculate the segment offset with the files. The segment offset is instead of this partition ID, we calculate the index that the file will be. So because this file is number 0, take 2, so the next file will be start at 2. And this file number 9, take 2 space, so the next file will be on 4. And this file take 1 space, so the next file will be at 5. In other words, the accumulation of the size of the files. So we accumulate that. And this is the file ID, where 0 also represents empty space, and the number of space needed for that file. Then we calculate the checksum from that. In order to do that and make it make sense, I create two data structure, two struct, which is files and segment. We can use tuple, but the code will be difficult to read. So let's do this instead. As you can see, the file is the file ID and the size. The segment is the index and the file which contain these two, and the flag that it has been moved. So to do the defragment without expanding, we first start with the line, and then we create this input. Well, we actually should call it this map. I'll rename it. Okay, after rename, now this becomes this map. Then we calculate the file size, which is this map divided by 2 plus 1. Then we create file segment. So we use another feature in functional J, which is the step. We start from 0 and step 2. We only want the file count. So this will give us 0 and 2 and 4 and 6, 8 to whatever the number of count that you need. And then we use that index to get the value from this map. So in this case, I use the helper function here. Then I map each value with its index to create files. Right? So at this point, because we only step from 0 by 2, so we only get the files. Right? So its index will be the file ID. So as you can see, this is another way to get the file segment. But instead of using as the index item, which is normally this one will produce, we ask it to produce a file instead, because what we got is the index from the position it's written in and the file size from the disk map. From the file segment, we can reverse it and get the segment reversed. Now, in order to move files, we call this move file function. We give it the segment ID, the disk map, and the revert ID. So you can come and see here to move file. It just determine where the file will be moved. This method, move files, will get the segment ID, the disk map, and the segment in reverse. Then you will get the file at the segment. So we get the segment ID, get the files, get the file ID, get the index of which the file currently is, which is 10.2, and then we get the file size. And then we go from the front of the disk map. So loop from the front, starting with 1, because we ignore the 0. And then we see if the available space, we also step by 2, and then see whether or not the available space is enough. If it is, we just save the index out here, and then we see if the index equal to -1, that means we don't find it. And if the index is greater than the index of the current file, we do not move the files. So we just return whatever it is right there without moving anything. Otherwise, set the file size. We subtract the file size at that available index. In other words, it consumes. So this map is consumed. So it reduces the available space by 1. And then we send out the segment as for that available space and the file. So this way, we send out the data structure that hold the segment ID, the files and whether or not it has been moved, so that we can collect them and use it later. I hope this is understandable. I know that a little bit difficult to understand. And then the next is to calculate the left empty space. So calculate the left empty space is just going to the move files and then only see the one that's moved. Get the file itself, get the index of the file, which is the file ID times 2, and then we create that segment, right? So replace the file with 0 to mean empty, and then it's not moved because it's stay put. And the next step is to determine unfilled space. And to do that, we only need to go through all the empty space, like at the beginning. So we only get the one that is at the on. And then we see that the empty space does not have more empty space needed. Sorry, if it's 0, that means have no empty space needed. But because it's not 0, so we will, this method, this call will return the func list of the file that will stay empty. I mean, then we create the empty, unfilled, empty space. Once we get that, we do a combine of that 3 things. So combine these 3, and then do a sort by the segment index. Then we calculate the offset. You can see the data. Offset is just accumulating the size. So add 2 size into the one before, we get 2. Add 2 here to get 4. Add 1 into this, we get 5. Add 3 into this, we get 8. So that means we just going through all the file size, and then we accumulate them by sum as an int. But because the first index is 0, you can see here. So I prepare it with 0. Then we get the segment that contain the files. So we go to the output segment, because the output segment is here combined, right? And then we map to the file. So we get segment, the file of each segment basically. We then zip the segment offset that we accumulate, right? Or the sum of the number here, or the number here. We zip it with the file itself. And that's what we got here. Then we calculate the weighted sum from that. That is it for the step. For part 2, once we change to the unexpanded method, this one only in mere seconds. If you see all this code, you can see that it kind of functional because you calculate things, put into value. This value never change. Calculate things like this. You can see each of these step. That is it for today. Puzzle of day 9, Advent of Code 2024. This is it for part 2. Just a reminder, all the code will be in GitHub. The link to that GitHub and the link to functional J and everything else will be in the video description. If you learned something, please click like. If you want your friend to learn too, please share. And if you want to see more, please subscribe. Either way, thank you for watching. See you again later.